The complex roots of a transcendental equation. The roots of an equation. Let's examine a quadratic equation, such as ax squared plus bx plus c equals 0. In graphing a quadratic, we get a parabola, a U-shaped curve, which can cross the x-axis at most twice. So, when it crosses the x-axis twice, we say it has two real zeros, or two real roots. The x-intercepts of a graph indicate the real roots, and quadratics have at most two real roots. This is also indicated by the largest power of x being 2. Now it is possible for a parabola just to kiss the x-axis, in other words just touch it, and that would indicate one real root. But because we say that quadratics have two roots, we say this root has a multiplicity of 2. Or another way to say that is that it is a repeated root. And that can be seen by a factor of x minus that root r, all raised to the second power. But what happens if we have the case where the parabola never touches the x-axis? Well, that's the situation where we get something called two complex roots. Two complex numbers that serve as the roots of the equation. Z equals x plus iy, where I is equal to the square root of negative 1. And complex roots always come in complex conjugate pairs. That is, if z equals x plus iy is a root, then its complex conjugate, z bar, x minus iy, will also be a root of the equation. So they always come in conjugate pairs. Now for quadratic equations, we can solve a quadratic equation using the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And the part that is of interest here is the b squared minus 4ac, the thing under the radical. That's called the discriminant. And that number, that value that we calculate, if it happens to be positive, indicates that there'll be two real roots. If that discriminant is equal to 0, we'll have exactly one real root, and if it's negative, we'll have two complex roots, and that's because you'll have a negative number under the square root. Now, by the fundamental theorem of algebra, a quadratic equation has two roots, and so an nth degree polynomial will have at most n number of roots, n number of zeros. Now for complex numbers, you have a number of ways that you can represent them. X plus iy for z, and then z bar is x minus iy. And you can also plot these on the complex plane, where the y-axis is the imaginary axis. So in other words, z equal to x plus iy would live in the first quadrant, and if I were to graph its complex conjugate, it would merely be a reflection of that complex number in the real axis, or in the x-axis. So complex conjugation is a reflection in the real axis. The length or the distance away from 0 that a complex number is called its modulus. And complex numbers can be represented in their polar form using Euler's formula, z equals r e to the I theta. Now, putting this together, the fact that complex numbers always come in conjugate pairs, and that complex numbers also have a modulus or length or radius, we can now examine the roots of a transcendental equation using some ideas with complex numbers. We'll now examine the complex roots of a transcendental equation. Consider the equation. 1 plus 2x multiplied with e to the x minus x equals 0. Now the e to the x part of this can be brought to one side of the equation, and we can rewrite this as e to the x equals x over 1 plus 2x. And this is our transcendental equation. The transcendental part coming from e to the x, which is represented by an infinite power series. An infinite power series can be thought of as an infinite polynomial, or a polynomial of infinite degree. And if this polynomial has an infinite degree, which is one of the reasons it's transcendental, then we can assume that it has an infinite number of roots, an infinite number of zeros. Now, we can examine something about the roots without actually finding them. On one side of this equation we have an exponential, and on the other side we have a rational expression. If we were to graph both of these things separately on the same xy plane, we would be looking for the points of intersection to solve this equation. So let's graph first y equals e to the x, which is always positive. It's never equal to 0, and therefore there's a horizontal asymptote at the x-axis at y equals 0. Now y equals e to the x will have a vertical or y-intercept of 0, 1, and we'll sketch the curve of e to the x in there. Now, for number 2, we're going to graph the other side of the equation, which is x over 1 plus 2x, a rational expression. And when looking at rational expressions, you can find the horizontal asymptote by asking about its end behavior, or what happens when x goes to infinity. And taking the limit as x goes to infinity of our rational expression, we get the ratio of the leading coefficients to give us 1 over 2, or 1/2. And if you have a hard time seeing this, you can divide all the powers of x by the largest power of x, which there is x. So if you divide the top and bottom by powers of x, you'll see what the value will come out to be. So we have a horizontal asymptote at y equals 1/2. The vertical asymptote would be where this rational expression is undefined, and that would be by setting its denominator equal to 0. Here we get x equals negative 1/2. So we have a vertical asymptote at x equals negative 1/2. Now, noting that our rational expression will go through the origin at x equals 0, and noting that it will go along the asymptotes, we can sketch our graph here and see what this rational expression looks like. One thing that we can note here is that we're looking for where y1 is equal to y2, or where the exponential equals the rational expression. Do they intersect? And the answer here is by visual inspection. You can see that clearly no, they do not intersect. Therefore, we can draw the conclusion that there are no real roots. There are no purely real roots. So we may not know what those roots are, but we know that there are no purely real roots. All of them must be complex numbers. Now, just because the solutions must be complex numbers doesn't mean we stop there. In fact, starting with the fact that z is equal to x plus iy, where I is the square root of negative 1, we recall that if z is equal to a root, then so is its complex conjugate z bar, or x minus iy. And so we can use that in our investigation to narrow down just exactly where these complex numbers might be. So that is, if we let f of x be our function 1 plus 2x times e to the x minus x, and if z is a root, then it'll make that function equal to 0, and so will its complex conjugate. Alright, so then we must explore a few cases with the complex numbers. Namely, the next thing we might try is to see if there are only purely imaginary roots. Now, a purely imaginary complex number means that the real part of that complex number is equal to 0. In other words, the root will live on the imaginary axis. So by letting x equal 0 and letting z just equal iy, we can substitute into our function and create an equation set equal to 0. Now, making this equation look a little nicer, we can bring the iy to the other side of the equation. And now what we'll do is we'll employ some absolute value approximations here. Absolute values are a critical tool in analysis. Now we can split the left-hand side into the product of two absolute values, and then the right-hand side can be also split into the product of two absolute values. E to the iy as well as I both have a magnitude of 1, so we can just assume them to be 1. And the absolute value of a complex number can be found in this case to be 1 plus 4y squared under the square root, and on the other side, by definition, is equal to the square root of y squared. Now, solving this equation gives us y squared equals negative 1/3, which implies that y cannot be a real number. And if y cannot be a real number, then our assumption that the root is purely imaginary cannot be true. Therefore, there are no purely imaginary roots. So up to this point, we've proven that all the roots are neither purely imaginary nor purely real. They must all be of the form z equals x plus iy, where the real part x is not equal to 0. So now we just let z equal x plus iy, where x is not equal to 0, and let's see what happens when we substitute into our equation. Now, by letting z equal x plus iy and making some substitutions here, we can use Euler's formula to split the exponential part here, or the transcendental part. E to the x plus iy power can be split as e to the x times e to the iy power, and the e to the iy power can be broken up into its trigonometric components. And so we can clean up this equation a little bit and write this more like two equations, one for x and one for y. And this is done by splitting it into its real and imaginary parts. So now we have this set of transcendental equations, both with e to the x in it and also sine and cosine of y. And from this point on, we would have to see if this holds true if we take the complex conjugate of z. In other words, if z is a complex number is allowable to be a root, so is its complex conjugate. So these equations must hold true for the complex conjugate. So let's see what happens under conjugation. We'll let z go to z bar, or we'll let change x plus iy to x minus iy. Really, that's just going to make a change of y to negative y in these equations. Now, cosine being an even function, the cosine of negative y is equal to the cosine of y. And sine being an odd function, the sine of negative y is equal to the negative sine of y. So making those appropriate substitutions, replacing any y's with negative y, we wind up seeing that both of these equations will be satisfied in terms of being true. They will work out to be exactly the same two equations. So by making a change of y to negative y, those equations never change, which only supports the fact that the complex conjugate is also a root. Again, since both z and z bar must be roots, we have confirmed that our roots must be complex numbers here. Now, determining which complex numbers they are, where do those complex numbers live? Well, we know it can't be x equals 0, but is x positive? Is it in the positive real range, or is it in the negative x real range? So the next thing we do is we observe for a root z that if we were to take the reciprocal of our equation, e to the negative z equals 2 plus 1 over z, and since z can't equal 0, this equation is satisfied always and defined, we can let the left-hand side of that equation equal capital T and the right-hand side equal lowercase t. So we have the equation capital T equals lowercase t. And that would mean that the absolute values of those things are equal as well. Now, taking the capital T absolute value, which is equal to the absolute value of e to the negative z, and breaking down to its components and their absolute values, we see that the absolute value of t is equal to e to the negative x. Now, if x is a positive number in our complex number, then the absolute value of t is 1 over e to the x, which is less than 1, so the absolute value of t must be less than 1. Also, if we look at what happens with our lowercase t, by substituting z equals x plus iy and doing a little bit of algebra by multiplying the top and bottom of that fraction by the conjugate and working out some of the details here, and then taking the absolute value and squaring it, we get the following expression. And if we take a look at what this expression says, that if x is greater than 0, then the square of lowercase t absolute value is going to have to be greater than 4, or the absolute value of lowercase t has to be greater than 2. And so now we have these three statements which are in contradiction with each other. We start with the absolute values being equal, then one becomes less than 1 and the other one greater than 2. So it's a contradiction that our x value in our complex number is greater than 0, and therefore the x value must be in the negative real range. So f of z equal to 1 plus 2z e to the z minus z equal to 0 that we're trying to satisfy here has complex roots z equals x plus iy, where x is negative, less than 0. So this tells us something about the nature of the roots. It means that all the roots must lie strictly to the left of the imaginary axis. So if we sketch this idea out, here's the real axis, here's the imaginary axis, we have only roots to the left of the imaginary axis, nothing to the right. But are we finished? Can we do more? Well, without actually solving this equation, what else can we say? Well, if we know that the complex roots have to live in this region, let's make z equal to negative x plus iy, where x is a positive 0, or greater than 0, So the absolute value of capital T is e to the x, where lowercase t works out to be this expression, and lowercase t in absolute value squared is equal to this expression. And what we can observe about that expression is that that last term is always positive. So we can make an argument here that the square root of lowercase t squared is less than 4 plus that positive value, which is less than 4 plus 1 over x to the fourth, which would be larger than x squared plus y squared to the squared. And so if x is greater than 1, the lowercase absolute value of t would be less than that square root, which would be less than the square root of 5, which would be less than about 2.5, which would be less than e. However, we now have the absolute value of capital T equal e to the x, and if we let x be greater than 1, absolute value of t is greater than e, and the lowercase absolute value of t is less than e. Another contradiction, which tells us that our assumption that x is greater than 1 in that negative x plus iy case is false. To spell that out a little bit clearer, we've just now found that our solutions must live in this narrow little band, this critical strip in the complex plane between -1 and 0 on the real axis. All infinite number of roots must live in this particular region. And even though we haven't solved for what those particular roots are, we've been able to deduce all of this through a little bit of logical reasoning in the complex plane. Now there's much more to be mined here, and I leave it up to you to figure it out. I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos. Stay tuned.